outside, yeah. That's what
Just keep them.
I probably need to pay that receipt.
you might, yeah. Probably should. Well, if you have one, you get one free one, but you lose bonus points. And then the second one after that, that's when
Yeah, I definitely owe you.
you right now, I think only Mitchell. All right, from this term.
Did you say I owe you time?
Yeah. Weren't you late twice?
I know I was late once.
January, 2 days in a row, I bet you. 21st, and, oh, maybe you talked to me about that second. The 21st and 22nd January.
Just keep.
Maybe one was like Saved by the Bell kind of thing.
I don't think so. I think he was late.
Oh, wait, no,
I remember he was late.
Oh yeah.
yeah. You and Justin, I think both were. Justin talked to me, actually. You talked to me about it. Yeah, that one. Yeah, that's right. I think both of you were. All right. Anyway, now let's go through what we have. Now we got thrown off a little bit with those snow days. Typically, on my plan, I had quiz tomorrow, which with 2 snow days would push it to Monday. The problem with that was actually in the plan was the quiz Thursday probably could have been Wednesday today, but it would have been. I think I had down about probably 15 minutes worth of just kind of finishing up, answering some questions, that kind of thing, and then mostly going on to new stuff. So under that plan, that would be Friday. Friday would be kind of wrapping up a few things, but then moving on to new stuff. And then the problem is the assignment then is new stuff, and there's really no review or anything for the quiz. Then you got the weekend, and so doing all of that and then having the quiz on Monday, I think is probably not the best scenario. I think we'd be better off doing the quiz Friday, and so that's kind of what I'm leaning towards doing. So right now we're going to plan on quiz Friday. We don't have a lot of new to do. It's more about this notation and what we've been talking about here. So we'll get a lot of that done today. We'll really get a lot of, wrapping up that all up and stuff Thursday. So it may be a situation where, if you've got some additional questions before the quiz Friday, based on that Thursday night's homework, you may need to get in there in the morning, get in here at lunch, before the quiz on Friday, okay, to wrap those things up. So that's probably what's going to happen. I've kind of cut out a little bit of something that I normally might have put on the quiz to kind of compensate for that as well. So that is the plan, okay? Sections 1, 2, and 3, we're in section 2 now. We'll be doing section 3 tomorrow, although we're kind of getting into section 3 today as well. And we'll still have one other thing to talk about with that tomorrow. Okay? So that's the plan. Plan on that for Friday. So let's look at your homework here and let's talk about these things. So right at the end of the day yesterday, we had a little f function, a little different than this one. And it looked like this. Now, I don't know if no one came in this morning and asked me about it, so I don't know if this confused you at all, but they gave you the function a little differently in this problem than we had done. And I want to make sure everybody's okay with that. They gave it to you like this, right, in the red over here, as opposed to this. Now, does everybody see why that's the same? Because if little f of x is equal to x, what's little f of t? That's t, right? So when they give you that right there, little f of t, they gave it to you as little f of x equals x, because, right, that's fine. You can use x here. But when you stick it inside the integral, where you're using x as your right edge, remember that's what we did yesterday, we talked about x being that movable right edge. As soon as you stick it in here, you're already using x for that, you can't use x again, so you gotta use something else. So that's why it would look like this. So I went ahead and wrote it this way, but they gave it to you that way. Those two are the same information, okay? So this would be the graph of y equals t right here. If I assume this is my little f axis, this would be the t-axis then, essentially, okay? And so they want to know the area from 4 to x, which would be this trapezoid. Now, what they asked for was the formula for that. Now, before we go through this problem, let's just recap, since we're thinking about Quiz Friday, let's recap what we've talked about so far. We've learned about this thing called the definite integral. Now, our first order of business with definite integral, or integral, was just this, from 3 to 5. Now, if you're doing that, that's just a fixed piece of area from 3 to 5. And so what letter you use in here doesn't matter at that point, right? It could be X, T, U, whatever, it doesn't matter. So that's the area under this curve from 3 to 5. And that's just a number, right? And we can calculate that, especially if it's geometry shapes, trapezoids, triangles, rectangles, stuff like that. So that was the first assignments we had, and there will be some of that on the quiz, where you just have, here's a picture, maybe some lines and some whatever, and you've got to calculate some areas using trapezoids, triangles, and that kind of thing. So that's the very first thing we did. Those are called definite integrals. Now we've moved on to using the integral as a function. Much like we went from calculating slopes to then talking about derivative functions, right? And slope functions. And we got into all that. Now we spent a lot of time getting into that because that's the first time we've seen it. Now we can kind of pick up the pace on that because all these things we're doing kind of connect back to what we had done earlier. So now we're saying that we can talk about area as a function. Every time we move this right edge, we get a new area. Move the right edge, get a new area. Move the right edge, get a new area. And so therefore, we get a function. Right edge is the input, new area is the output. That's our function. We call that an area function. We use big A of x, in this case what we've been using, to talk about that area function. All right, so problem 2 wanted you to write a formula for this area function. Well, it would, since this is a trapezoid, all we need is a trapezoid formula. So, what is this base right here? That would be 4. What would be this base over here? That would just be x, right? Because the function is y equals x, so if you plug in an x, you get out an x. So this would be 4 plus x. And then times the height of this, which would be x minus 4. So there's your trapezoid area, and this would be 1/2, and then if you multiply this, you get x squared minus 16, and we multiply that through, we get 1/2 x squared minus 8. Now, the big aha moment yesterday was, that is what? The antiderivative. Now, we've been hinting at it all the way along, clear back to the very first day when we did a velocity curve. We did the area under it. We saw we got position. We're like, oh, that's antiderivative to go from velocity to position. So it's not a huge surprise that we get antiderivative. What is kind of cool is that we just did an old geometry formula to a picture, and lo and behold, what came out at the end was an antiderivative. That part is the part I think is really cool and amazing. How in the world did that come out to be an antiderivative? The only difference, the only thing we don't know, so you go back to little f, when we say antiderivative, we mean of the line we were doing the area under. You look at x, what's the antiderivative of that? It'd be 1/2 x squared, but when we normally do an antiderivative, we do what? We tack on a plus c. Well, there's the plus c, the minus 8. Now, the only question is, what caused that plus c? In other words, what would I have to do to this picture to then work it out like I did here and get a different c? What would have to change?
Oh, wait, no, the 4 would be
The 4. That is the key. Now, we haven't done one. We'll do one here in a little bit where we do that, but I think you're right. I think it's the 4. If the 4 changed, we would get a different plus c. We'd still get the 1/2 x squared, I believe, because it's still the same little f, right? We're not changing that. So if we think, if we move the left edge, then we would get a different plus c. And I believe for sure that you are correct with that. All right, let's move on to let's see, that's not number 3. In your book here, number 3 through 8. Okay, let's take a look at those. Now, what we're told here is we've got the big A is equal to the integral from 0 to x. So 0 is our left edge. So we are, well, we got a short class today. Hurry. There we go. All right, here's our left edge right here at 0, and our right edge is off over here somewhere. Now, this is little f. Is big A of 1 or big A of 5 bigger? Well, I'm mostly interested here in not only your answer, but your reasoning, because this is the type of stuff I want you for sure to be able to do on the quiz. This is the type of understanding of the concept of what's going on here, of the notation and so forth, that we could give this rationale. There are multiple ways we could explain this. Ryan, you said 5. Why? Okay, and you might want to say a little more. If this was a quiz question, you might want to go a little more detail on that. I like the word positive. That's a key. You might say since F is above the x-axis or something, but that's pretty good. But the area, I suppose the other thing we could elaborate a little bit is this. What is A of 1? It's the area from 0 to 1, right? I think putting that down would be a good thing. A of 5 is 0 to 5. Right, and since little f is above the x-axis, the area is always positive, right? The picture wouldn't help. This has more positive areas, so A of 5's got to be larger. Did anybody actually calculate the areas? Now, somebody in the other class did this. Somebody in the other class, they were going to do A of 1, so they said, well, that would be this piece of area right here. Isn't that correct? And they actually did a trapezoid calculation. It's not a trapezoid, but it would be pretty close to a trapezoid. And to be honest, the only other way we could find this area is just approximate it anyway. So if you did a trapezoid, it would be like approximating. I would say that's more work than necessary. I think just count squares, right? I think if you're going to approximate, just say, well, each one of these is 1 because the grid is 1 by 1. So 1, 2, 3, almost 4, 3.8, whatever, something, I don't know, approximately, not equals, but approximately. And then this one would be about 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, maybe 18, 19, 20, maybe, approximately. So clearly that one's bigger. So that would be another way you could do it. You could actually calculate, because this is a really key thing I want you to understand notation. A of 1 is saying put a 1 here, which means put a 1 here. So it's the area from 0 to 1. Okay, so that's how we can answer that. But I like the fact you said that with area. And then number 2 is what? Kind of the same thing? 7 or 10.
Yeah.
So 7 is, because what happens between 7 and 10? You pick up negative area. So here's another visual that I think is really helpful here, is envision the X, the right edge, when I was dragging that yesterday. Remember that gold area, that yellow area was showing up? If I was doing that here, if I stopped at 7, I'd have all this positive area, plus a little negative, right? Plus a little negative. And then when I go on to 10, I would be picking up even more negative, right? And I pick up even more negative. That's got to be going down, right? The area function's got to be going down. You got your homework? Okay. All right, so A of 7's got to be bigger. Now, here's the thing I'm not sure you probably thought of, but here's one of the big points of emphasis today. And that is this big discovery yesterday, or the last few days, has been what? That the area function is what? The area function is the antiderivative of this function. Therefore, this function is the derivative. So isn't this kind of like an f prime graph, and they're asking me about f? And so let's do it that way. Here's f prime. What's bigger, f of 1 or f of 5? Why? Since f prime is positive, f is increasing. Since f is increasing between 1 and 5, f of 5 has to be bigger than f1. Isn't that right? So a big part of what we're learning here is not a bunch of new stuff, but a new way of looking at old stuff, right? Because we've made this antiderivative connection, all that stuff we learned about the chart. Remember in the beginning, and we had all those connections, it was really confusing, and then we made the chart, we organized it, and then we used it a lot, now it became more clear. Well, the nice thing is we don't have to go through that whole confusion stage, really, because, yeah, the notation kind of gets weird sometimes, and we got to work our way through that. But at the end of the day, just all you have to really do is to keep coming back to, hey, this is this antiderivative connection. Area is the antiderivative of the little f graph here. And so therefore, all those things we learned before are still true. All those chart connections are still there. It's a new way of looking at our old stuff. So you could actually, on the quiz, you could have used that reasoning. You could have said, well, the area function, big A, is the antiderivative of little f. So therefore, since little f is positive, big A is increasing. You know what I mean? We can still use those slope derivative rationales for the chart, but I like the fact you were talking about them as areas, because that's what we're doing now. I really would like for you to talk about them as areas, to be honest with you, as your explanation. But it's not wrong to talk about them with slope connections too. And if you're unsure, put them both in. But I really want you to see both, because I may ask you a question where I word it in such a way that you have to answer right from an area perspective, right? So, but if not, if it's just asked like this, right, you can answer those questions that way. All right. So it's cool how all these things fit together. All right. Why is A of -1 less than 0? Because it's moving backwards, right? This area here, normally that'd be positive, but when we put our -1 in for x, it goes up here. So we're doing the area from 0 to -1. That's going this way. That's backwards, okay? Well, that does, everything becomes opposite then when you go backwards. What? Is that 2 days in a row for you? Weren't you late yesterday? All right, so 0, -1 is going backwards, so it's got to be negative. All right, what's the next question? Is big A of 8 positive? The area from 0 to, is that the next question? Why am I on the wrong page? No, I'm on the right page. Are we on number 6? Is A of 8 positive? Right? That'd be the area from 0 to 8. What? More positive area than negative area. Now, back in the derivative days, we just said because little f is positive for a long time and then negative for a little while, so the big A graph would be going up for a long time and then coming down for a little while, right? And so it's going to be positive, right? Well, actually, we probably need more. We need more than that. We need to know what? Where it starts. We need to know where it starts. Now, you know what? This is as good a time as any to say when it starts. I was saving this actually, but we'll use it here later on. Here's the big A function right here. Okay. We just said big A of 8 we think would be positive because we gain all this positive area and then we have a little bit of negative. So you add that up, that's definitely going to be positive. So how can we know that, but if we think of it in terms of slope, we don't? Well, we just said we don't know where it starts. Well, I disagree. I say, remember when we did differential equations, which kind of could involve an antiderivative? There's a plus c usually when you do an antiderivative. How do we find that plus c? What do we need to find that plus c? An initial condition. I say that when you're given an area function, you get a free initial condition without even knowing it. You know that A of 0 is 0. On the one we did earlier today, where we were given A of x was equal to 4 to x, didn't we know that A of 4 was 0? Sure we did, right? Because the area from 4 to 4 is 0. We know that every time. So when you're given an area function now, not only do we know it's an antiderivative, which would have a plus c on it, and we thought that a different left edge would change the c, well, that just kind of showed it right there, didn't it? That if you change the left, because we get the antiderivative with a plus c, we can actually find the plus c because every time if we know the left edge, we know at least one area on there. We know when its area is going to be 0. That's like an initial condition. See? So that's another thing that connects back to kind of some old stuff. All right, moving on. Well, so what we would know is we would know A of 0 is 0. So we know the area graph would start at 0, 0. And then since it's increasing for a long time, it'd be positive.
So then on the other one, it would start at 4.
Right, right. All right, so now, A of -2 or A of -1, well, that's one we were saying was going backwards, right? So which one's bigger? Well, if you go backwards, you pick up negative area, and then you'd pick up some more negative area. So the graph would be going down like this, right? So which one's bigger? The one at -1. Okay, good. And now let's talk a little bit about A, because several of you had some questions. Let's pretend we have a new left edge. So what's that mean? Well, we're going to have a different plus C, right? So explain why this is, and explain why C would be negative. Well, first of all, two antiderivatives. If you think of the first problem we had today, we had little f was x. What's the antiderivative? 1/2 x squared plus c. Won't every antiderivative be that? The only difference between any of the antiderivatives is the different c value. It's the only difference. So that's what this is saying. This is saying, well, big F, if you're going to use the same little f, then big F has to be the antiderivative, just like big A was the antiderivative. So they're both antiderivatives. The only difference between them is a c value. That's what this line is saying right here. That these two things are equal except for some constant added on. Now, which one do you add it on to? Doesn't matter, but will C be negative or positive? Will depend on which one's bigger. That's how I like to think about it. So if we start at -2, so if the F graph is starting at -2, let's do it this way. So they asked me this. They said, okay, show that A of x is equal to big F of x plus C. Well, A of x starts at 0. A of x does, right? So here's x. So here's A of x. And let's have F of x be the blue because it starts at -2, right? Wouldn't this be F? Yeah, so wouldn't big F be the blue? So which one of those is bigger? The blue, right? And why is it bigger? It has this little chunk of positive area that the A doesn't have. And even if I slide the x this way, will that change? That little piece of blue will always be there. And even if I slid it back this way, the difference between them would still be this. Now, it gets a little more confusing when you slide it the other way, but just trust me on that. But if we slide it this way, we keep sliding this, the blue and the red will keep growing, but they'll always have this difference between them. So if you change the left edge, we said that changes the C. They're still both antiderivatives. They will always have that difference between them, between their left edges, right? And that's always a fixed piece of area. It's just the piece of area from -2 to 0. And that won't change. It's a constant. And since that, so, here's how I would answer why this is, here's how I would answer it, and maybe there's some other ways too. I like to, when I see two things are equal here, or almost equal, I would say, okay, the blue is bigger, right, than the red. We all agree on that? So how can they be equal? If you take away something from it, right? So C is going to have to be negative. Big F is a bigger piece of area than big A, and the only way they're going to be equal is if C is negative, because that'll take away, and it's going to be negative by what amount? That amount of blue area right there. You take away that piece of blue area, and then they'll be equal. So that's why C has to be negative, because you have to take away that piece of positive to make them be equal. A lot of times people say C is positive because they'll say, oh, the difference between them is this piece of positive area. Oh, that's what the C is. So they think C has to be positive. Well, it depends which side it's on. If the C was on the A side, then what would it be? Positive, because big A is littler, the red area is littler, so if you add on that positive area, then they would be equal. See the difference? So that's where that question you have to kind of think about. All right, now let's go to 9 through 11, and that's where I've got this picture right here. So what they told you is that little f was always greater than 1. So that's why I drew this line right here. So let's just imagine little f just being up here, something like that. It's just always going to be above 1, which is nice because it means our area is going to be positive, right? It means our area is going to be positive. So that's what's helpful in these questions. Notice, and you're going to notice this on today's homework, you're going to see some of these same kinds of questions over and over. They're just asking you different types of questions in these same scenarios. It's just new ways of looking at old stuff. Okay, so you're going to keep seeing some of the same stuff. We're just trying to get familiar with this notation. But the underlying principle is the key, that the area function is the antiderivative of the little f graph that we're doing the area under. So, different left edges. So the only difference between these two should be the C, the constant, the area in between where? 0 and 5. The only difference between these two functions is that piece of area between 0 and 5, right? The plus C. They're both antiderivatives, the only difference plus C. So if I talk about the F graph, it would be this blue area. Let's put X over here somewhere. So here's the F area, right? And let G be the red. And so G is going to be, let's put 5 right in here. Okay, so G is going to be that piece of area. I think just pictures are helpful to help you think about it. All right, so when they asked me a 9, is big F of 7 greater than big F of 1? I'm talking about the blue now. Yeah, because big F of, again, that's the same as question 3, isn't it? Big F of 1 is the area from 0 to 1. Big F of 7 is the area from 0 to 7. Since those areas are all positive, you've got more area on this one, right? The slope reasoning would be little f's the derivative. It's always positive, so big F's always increasing. Again, that rationale would work as well. Number 10, big G of 9 greater than big G of 5. Well, what's big G of 5? 0, right? And big G of 9 would be some additional area, positive area, so big G of 9's got to be bigger. And then 11, why is big F greater than big F of 0? Well, what is big F of 0? Big F of 0 is the area from 0 to 0, which is 0. So basically this question is saying, is big F positive? As long as X is positive, so as long as we're going this way. Sure, because big F starts at 0, and so you're always going to get positive area, right? No matter where X is to the right, like that. Okay? So, that's, again, just a lot of different ways of asking those questions. Now, 12, 13, 14 are the same scenario. Those are going to be part of tomorrow's homework. And just doing this. And a lot of the homework is going to be similar stuff to this. Now, let's move to this scenario right here. This is on your assignment sheet. I think I had said, yeah, on your assignment sheet, I had put that we were going to do 21 through 28 in class. Now, so what I'm going to do is I'm going to do 21 basically, and then I'm going to give you some additional pieces to do this. Now, this is one of the parts I'm going to take off of the quiz. So I don't know that you need, what I'm about to write up here, I'm not sure you need to copy all down with me, but you might go ahead and draw this picture, and you might write what we have here. Now this first part I'm going to do just like we did in problem number 2 for today. With that trapezoid area, you're not going to have to do that on the quiz. Okay? Because what happened when we did that trapezoid area? What did we end up with for our formula for the first homework problem today? Antiderivative, right? You know that's going to happen now. So it kind of takes the surprise out of it. It kind of takes, why even go through that all, okay? Because you know you're going to get the antiderivative. Why couldn't we just use our antiderivative rules to do it, right? And I agree. Not only that, but here's the other reason I'm not going to make you go through and do it, is because it works on such a small number of functions. If we had a parabola, could we draw a trapezoid or something under there and do this? Like we did on number 2 today? No. Hardly on any functions can we do it. The only ones we've done it on so far are horizontal lines and diagonal lines like this. That's the only type of functions this work on. But it's really cool to do on those because I'm still amazed after teaching this for 15 or more years, twice a day, that this comes out this way, that it comes out to be the antiderivative. I just think that's awesome. So I love doing it and showing it, but it's not that practical for an everyday use kind of thing. So I'm not going to make you do it. So I'm going to run through it real quick. You guys help me, and then I'll tell you the part that I would have you write down and that you may want to be able to do on the quiz and on your homework. So I've got a new line. It's a different line than the one we did on our homework. We've got big F, big G, big H. They all have different left edges. So what do we know is going to happen? We're going to find a formula for big F, big G, big H. Each of those is going to be different, bigger than the other one. Well, because -2 and then 1 and 0,
They'll have
right?
a different C,
Different C value, but they'll all be antiderivative, right? They'll all be same except for the C. We know that's what's going to happen, right? Okay, so I'm just going to do a couple of them. I'll skip over G. Let's do F. We'll do that one in blue here. So F starts at 0, goes over here to X. Let's just put X over here. Okay, so this would be the big F area, and it's a trapezoid, right? Now, again, you don't have to write this down if you don't want to, because you're not going to have to do this. But this is just like we did with number 2. Okay, so it's a trapezoid. The only trapezoid you're going to have to do on the quiz would be if I give you a picture and say, do the area from 2 to 7. And it's a trapezoid. Then you have to be able to do that trapezoid area, right? That kind of thing. But not with these X's. Not going to have to do it. All right, so what is this base here? 2. Okay, what is this base over here? No. This would be 3x plus 2, right? This one is 2 because you put a 0 in for x, you get 2. This one is you put an x in for x, right? And you get 3x plus 2. So this height here is 3x plus 2. And then times the width or the height of the trapezoid, which is x minus 0, which is just x. Okay, so now this in here would be 3x plus 4. And now let's take 1/2 x times that. So we would get big F would equal, if we take 1/2 x times this, we'd get 3/2 x squared plus 2x. And voila, what do you notice? Compare that to little f. Isn't that the antiderivative? Never gets old. Raise that up to 2, divide by 2. Antiderivative 2 is 2x, 3/2 x squared plus 2x. Sure enough, we got the antiderivative. The C ended up being 0. Okay, now let's go to H. I'm going to do that one in red. Okay, now I know that this crosses at -2/3. Now that's something you might have to do. Let's understand something here. If I give you a line like this, or give you one, and I'm not talking about in this problem, but I'm talking about if I just want you to do the area from -2 to 5. And you see, and I give you a graph that crosses kind of in between. You need to be able to use the slope, kind of like that midterm problem we had where some of you estimated you should have been using the slope to get it more exact. You need to be able to use the slope, whatever, to find exactly where that crosses so you can find those areas. It might come out a fraction. So what I did here is I knew this was 3x plus 2, so I set that equal to 0 and solved it, and that's how I knew that crossed at -2/3. Okay, you need to be able to do those kind of things when we're doing these areas, okay? So anyway, that crosses at -2/3. Now this one goes from -2, so that'd be over here somewhere, okay, all the way over here to x, okay? So now this is interesting because this is going to give me a triangle and another triangle, right? Instead of trapezoid, I'm going to have 2 triangles, right? So let's do that area. So first I would have this first triangle. Well, what is this base here? What is the base of that triangle? What would that be? 1 and, would that be 1 1/3? 1 1/3, right? Is what that would be. What would this be down here? I guess I'd call that 4/3. Maybe. What would this be down here? -4. How do you get -4? You plug it into the line, right? Plug it into the line. So you put -2 in, you get -6 plus 2. This would be -4. Okay? So negative 4 times 4/3 is negative 16/3 times a half. So that'd be negative 8/3. Okay, plus, now again, don't worry about, right, you're not going to have to do this, right, so let's just run through it. Now, what I'm left with this triangle. So what is the base of this triangle here? What would that be? No. Would it be x plus? It'd be the right edge minus the left edge. It'd be x minus negative 2/3. It'd be x plus 2/3. Now that makes sense because x is from the y to here. That's x, and then plus you got an additional 2/3. Now, and by the way, this is negative area. Everybody agrees with that, right? This is negative area down here, and this is positive. So now, I need to times this by half. I forgot. And then times my height. What's my height here? 3x plus 2, right? My height over here is 3x plus 2. So that's 1/2 times base times height. Okay, now, let me go ahead and FOIL this. There's no way this can come out to be the antiderivative. What a mess. There's no way. Well, maybe. I don't know. Maybe. Let's FOIL this times this. So x times 3x, that's 3x squared. Outers would be 2x. Inners, what's 2/3 times 3? 2x. Oh, that's 4x. And then last times last, 2/3 times 2, 4/3. Now I got to take that all times a half. So I got negative 8/3 plus 3/2 x squared plus, plus 2x. 1/2 times 4/3 is 2/3. And then what's negative 8/3 plus 2/3? So I get 3/2 x squared plus 2x minus, look at that, antiderivative again. Like so. Never gets old. I just want to do that one more time because I just like doing it. But normally I have lunch in between second and third and I can rest a little bit. But man, this is 2 in a row. All right, so listen. So we got the blue. The big F came out to be this. Big H came out to be this. It'll happen every time. All right, you're not going to have to do that anymore. The result is what we care about. The fact that we know when we have an area function, it's going to be antiderivative, and different left edges is going to give you a different C value. And we also know that that C value is what? It's that piece of area between, in these two examples, it's the piece negative 2 and 0. It's this piece that's different between the blue and the red. How much is that piece? We said this was negative 8/3. How much is this? 2/3 times 2 is 4/3. Half that's 2/3. Negative 8/3 plus 2/3. Oh, negative 2. That's the difference, right? This is negative 2. That's the difference between these. The red has less area because it's got more negative, right? The red's got more negative, so it's actually got less area. So the negative 2 is taken off there. That's the C value. Now, so here's the important part that you want to be able to do for the quiz. So if we don't have to go through all that, right? If we don't have to go through all that to know what's going on, right? Because think about it. Once we knew little f was this, we knew big F was going to be 3/2 x squared plus 2x plus some c, right? We knew that. Before we did any of this, drawing pictures or anything, with just this and this, we knew it's the antiderivative. We could have written this. The only thing left is to find the c, and to find the c you need initial condition. And guess what? When you're given an area function, you get a free initial condition. We know that big F of 0 is 0. If you're going to write anything down, this is what I would write down. So we know that the antiderivative is going to be this, and we also know that if we put a 0 in for x here, we get the area from 0 to 0, which is 0. And now what do? We just plug that in. So we'd have 3/2 times 0 squared plus 2 times 0 plus c, and that's got to equal 0. Well, all that cancels out. So we get c equals 0. So sure enough, big F is going to be 3/2 x squared plus 2x. And we could have gotten all that way without going through the whole big trapezoid thing. And the beautiful thing about that is, what if little f was a parabola? Does my area way of doing it work? No, because it wouldn't be a geometry shape I could do. But we now trust it, I think, enough to know that that antiderivative thing's always gonna work. So I could have just, if I got a parabola as my little f, just do the antiderivative, tack on the plus c, take my initial condition, throw it in there, and I've got it. And so I can find my antiderivative formulas now for any area function because every area function gives me a free initial condition with it to find the plus c. All right, and then h, just for the heck of it, so we know h would also be this 3/2 x squared plus c. What initial condition do we have on h? We know h of -2 is 0, right? Because the area from -2 to -2 is 0. So I could put a -2, let's do it, 3/2 times -2 squared plus 2 times -2 plus c would have to equal 0. -2 squared is 4, 4 times 3 is 12/2, 12/2 is 6, 2 times -2 is 4, minus 4, plus c is 0, 2 plus c is 0, c is -2, voila, there it is. C came out to be -2, so we found it that way. So, really cool that we can do these areas, and that, you know, you do a trapezoid, do a triangle, and the antiderivative comes out at the end. Pretty neat. But the result is that area function is the antiderivative. We knew it yesterday. We've hammered it, and that's the big thing. So, here we go. Let's summarize it right now. So a lot of your homework today is going to be similar types of stuff, similar questions of 3 through 8, 9, 10, 11, right? Making sure we get this connection, and we can use our slope if we want to. It's chart kind of questions, right? Gonna just do a lot of different ones. So you have to just, and they're going to ask you different things and thinking about a lot of new ways to do stuff, do old stuff. But so if this is my area function, well, I'm going to call that big A. And we notice we've been calling big F, big G. Not a coincidence we've been using capital letters, right? Capital letters mean antiderivative. Okay? Now we don't have to, right? I've seen these area functions, I've seen those called like little g or something. And that just means little g is the antiderivative of little f. You can do that. It doesn't have to be a big letter to be an antiderivative. Okay? So, what have we learned? What's the connection between A and F? You've said it so many times, it's just like getting boring. All right, A is an antiderivative of little f. But here's where I'm going with this. I don't want to have to write that out. I want some notation we can use that says something's the antiderivative. What? One way to do it would be to say A prime is equal to little f. That's right. We could say A prime is equal to little f. Now the problem is, what if instead of calling it that, what if we want to just use that? It's hard to put a prime on this, right? I mean, where would you put the prime, right? So another way of saying A prime is this. The derivative of A of x is equal to little f of x, right? So that's a little more formal notation, but it's the same thing. And I don't want to gloss over what Kelsey said. That's exactly how we show something's an antiderivative. We say if you do the derivative of it, you get back the original function. And what happens to the plus c? Goes away. So notice I have a little a down here as my left edge. Doesn't matter what the left edge is. That just changes the c. When you do the derivative of it, that goes away anyway. Now, this is a big deal. I mean, geez, we've been talking about it for days. It's a big deal. Why is it such a big deal? Because it connects the two big parts of calculus. Back in the 1600s, when Isaac Newton and all them came up with this stuff, it was because these were two things that were being worked on separately. This whole idea of tangent lines was being worked on because there was a lot of astronomy and those kind of things going on, and optics like refraction and reflection, and so light comes in and hits this here, and it reflects, and this angle is equal to this angle, and so the tangent line to a curve, that was a big deal in the study of optics and so forth. So tangent lines to curves was a big deal being studied. And then also back in those days, in the 1600s, it wasn't as much about how much money you had, but money was more like property. It was landowners were the wealthy. And so knowing how much land you had was a big deal. So being able to calculate the areas of odd-shaped parcels was was a big deal. And so finding areas of odd shaped things was something they were working on. What makes those two things part of calculus is this connection, the fact they're connected. And this sentence connects it right here. This says that when you do the derivative of the area, you get the original function. This connects derivative, rate of change, to area. Okay? That's the big deal. It's such a big deal that they give it this fancy name right here. It is called the fundamental theorem of calculus. The fundamental theorem of calculus. Because it ties together derivative slope with area. Okay? Now, there's two parts to it. We're going to do the second part tomorrow. So this is part one of the fundamental theorem. It's just the idea behind the fundamental theorem. Now, notice how I've written it differently. I didn't put, because this is how it's usually written. It's easier to understand if you just call that big A in there, the derivative of the area function. When you see that integral with an x on top, you always think area function. Always think area function. Okay? Big A of x. But that's what it's saying. If you do the derivative of the area function, you get little f. Why is that? Because what have you been telling me all this time? The area function is the antiderivative. So really, the left side of that's like saying do the derivative of the antiderivative. Well, what should happen if you do the derivative of the antiderivative? Cancel each other out. And so what happens? You're left with little f. But notice, and this is the part that will get people, notice we have a t here, remember, because we have to, because of that x up here. So we have a t here, but here we don't. Here it's an x. Now, nobody would have thought of putting a t back on this page when I said the derivative of big A of x is little f of x, right? We would never thought of a t being anywhere in there. But all of a sudden, when I write it this way, we do. So be careful of that. Remember, there's only a t here because of it's inside that thing. Now, here's the only question I'll ask you about this notation right here, this thing right here. The only question I'll ask you, and on the quiz, it should be the very easiest question there is. There will be a question something like this. So if you want to write this down, you know, that'd be fine. But there'll be a question something like this. Some weird, crazy looking function in there. That'll be the question right there. What is the correct answer? It should be the easiest question on the quiz. E to the sine of x squared. Right? Because look what this says. This says, what it says is you're doing the derivative of the antiderivative. So on this problem, we're saying inside here we have the antiderivative of this. Now, do we know the antiderivative of this? No. It turns out there actually isn't one. We'll talk about that later. But actually, there's not a formula for its antiderivative. But don't worry about that now. But that's why I put something weird in here. Because if I put something like just x in here, right? If I just put x in here, you could work it out, the inside part. You could say, well, that's 1/2 x squared plus c. You could put your 3 in as your initial condition, right? You could find the c. You'd get 1/2 x squared. Think about this now. You'd get 1/2 x squared plus 10, and then you do the derivative of it. What do you get? 1/2 x squared plus 10. What's the derivative? X. You get back what you started with, right? So if you do the antiderivative, you get a plus c, then do the derivative. The c goes away. You just get what you started with. The difference is it's not a t anymore, though. It's an x, and that's a problem. If you put a t in your answer out there, you'll get it wrong, right? You'll get it wrong. So, again, what happens? When you do that antiderivative, it's like when we did that trapezoid thing. We didn't get t's in it. We got x's in it, all right? So derivative of the antiderivative, they undo each other. You just get that right there. But anyway, that's the fundamental theorem of calculus, which summarizes in notation what we've been saying all along. The area function is the antiderivative. All right. So if you want to get started on the homework here, here's what we're going to do. It's more of the same. Every one of those is kind of a group, or most of those are kind of here's a little f graph, right? They're kind of like 3 through 8, 9, 10, 11 were. Here's a little f graph, or here's an area function. And you know, answer these questions about it. They're kind of chart kinds of things, so they don't take terribly long, but it's a little longer than last night's for sure. And we really want to to get through this and understand this notation, it's important that you have a pretty good grasp of this as we move into tomorrow. And so we'll talk about this. We're going to add a little bit to tomorrow, but not a lot. There's not a lot to add tomorrow. So, we should be ready to go by Friday. But you're going to have to come in tomorrow morning or tomorrow at lunch if there's some of this stuff that you're just really struggling with. Okay? Each of those sections there are going to seem very familiar. They're going to be a lot of the same types of things. All right, so you got the last, 15 minutes here or so. 13, 14 minutes to work.